Okay. A small smooth ring R, smooth. So this ring is smooth, meaning that tension in both the strings around it, or tension in this part of the string and this part of the string is going to stay the same. So we're going to use T for both the tensions, not T1 and T2. Okay. And there's a zero point 0.6 kg mass of the ring. So this would be a 6 Newton force in this direction. One end of the string is attached to fixed point A. A small bead B of mass 0.4 kg is attached to the other end of the string. Okay, now this weight is 4 newtons, and since there's a contact between the bead and the rod, here there will be a normal contact force, unlike on R. Okay, so there's going to be a normal contact force, which is represented by R. Okay, okay. So a small bead B of mass 0.4 kg is attached to the other end of the string and is threaded on a fixed rough horizontal rod which passes through A. The system is in equilibrium with B at a distance of 80 meters from A. Okay. Notice you're given three lengths, this length, this length, this length. You need to use these to find the angles since there's no angle mentioned in the question. So I'm going to try and find this angle, which will be the same as this angle because this is an isosceles triangle. So instead of the angle, I think I'm just going to find sine theta and cos theta because that is what I need in the components. Okay, so if I make a dotted line here, and only because this is an isosceles triangle, this would be 40. Okay, and if I use Pythagoras on this, it would be square root 50 squared minus 40 squared, which should be 30. Yes, so this length is 30, meaning sine theta is 3 by 5 and cos theta is 4 by 5 because the zeros cancel out. Okay. Now, what do we need? Find the tension in the string. Okay, so I'm looking at this R here. Let's resolve all the forces. There's going to be a component of T in this direction and a component of T in this direction. And I'm going to draw that here instead. Okay. So this one is adjacent. So T, this is theta as well, by the way, from alternate angles. So this one is going to be T cos theta, and the opposite one is going to be T sine theta. So this would be T sine theta. Similarly, on this side, this would be the adjacent component T cos theta, and this theta is the same as this because of alternate angle. So this would be T cos theta, and this one would be T sine theta, which I'm plotting here. So another T sine theta. So we have two sine thetas in the upward direction. Okay, I believe I've written all the forces. Now let's equate them. This force is equals to, oops, the force, oh, how do I clear this? Okay, so this force is equals to this force. They cancel each other out because T cos theta is equals to T cos theta. We're not getting anything from here. Now, equate these forces. So this would be 2T sine theta upwards is equals to 6 newtons downwards. So 2T sine theta is 3 by 5 is equals to 6, which gives us T is equals to 6 times 5 divided by 6, so it's just 5 newtons. Tension is 5 newtons. Okay. Find the friction and the normal component of the contact forces acting on B. Just give me a second. Okay, part 2. Find the frictional and the normal component of the contact forces acting on B. Okay, now let's take a look at B. So at B, if the movement takes place, it's going to go in this direction because there's a pull from this tension here. Okay, so that means that friction is going to be in this direction, mu r, or friction. Let's call it friction because they did not ask for mu. They want the exact friction. Okay, friction is in this direction. We have a component of tension in this direction. Okay, so this is from B's perspective. Tension will be in this direction. So this is theta. So this would be T cos theta, and this would be T sine theta. Also, there's a 4 Newton weight in this direction, and there's a normal contact force R in this direction. Okay, now we need to find both friction and R. Let's find friction first. Friction is balanced since the system is in equilibrium. Left force is equals to right force. So that would be T cos theta. T is 5, cos theta is 4 by 5, so friction is coming out to be 4 newtons. For normal contact force, we're going to equate this R with these downward forces. So R is equals to 4 plus T sine 30, T sine theta. So 4 plus T was 5 and sine theta was 3 by 5, which gives us 7 newtons. In part 3, we have to find the coefficient of friction given that the system is in limiting equilibrium. In limiting equilibrium, we use this formula. Friction is equals to mu times R. Friction was already found 4 Newton. Mu has to be found. And R was already found 7. That means mu is equals to 4 over 7.